Here's the architecture diagram of our Wi-Fi based IoT project, where we have included additional use cases under the end nodes such as smart home, environmental monitoring, notifications, and control interfaces. These end devices send data to the application server through the internet after connecting to the network via the Wi-Fi router. To ensure secure communication here, the TCP/IP stack is used to establish encrypted channels between the end devices, Wi-Fi router, and the application server. In this architecture, end devices communicate with the application server. Through the internet using the MQTT protocol, a lightweight and efficient messaging protocol designed for IoT. MQTT supports fast and reliable publish-subscribe communication but lacks persistence and advanced routing features like those offered by the RabbitMQ, for example, exchanges, queues, and bindings. However, this simplicity is what makes MQTT highly suitable for the resource-constrained IoT environments like this. Now, let's talk about the limitations of our Wi-Fi based IoT project. The first limitation is it requires Wi-Fi infrastructure. This architecture depends on the presence of a stable Wi-Fi network. In areas where Wi-Fi access is limited, unreliable, or unavailable, such as remote outdoor locations, this approach may not be feasible without additional network setup. So this is the first limitation, and the second limitation is high power consumption. Wi-Fi communication typically requires more energy compared to the other low power alternatives. This makes it less ideal for battery powered or energy constrained devices, as it can significantly reduce their operational lifespan without frequent charging or battery replacement. So this is the second limitation, and the third limitation is limited communication range. Wi-Fi is generally limited to short range communication, typically within a home, office, or building. For wider coverage across large areas or in distributed outdoor deployments, additional infrastructure like repeaters or mesh networks would be needed, which increases complexity and cost. So this was the third limitation. So these are the limitations of our Wi-Fi based IoT project. Now, to overcome these limitations of our Wi-Fi based IoT deployments, migrating to a low power wide area network, LPWAN, is a smart and scalable path forward. Among the popular LPWAN technologies such as Sigfox, NB-IoT or cellular IoT, LoRaWAN stands out as the most flexible, cost-effective, and developer-friendly solution for a wide variety of IoT use cases. Now, let's talk about why to choose LoRaWAN. We will choose LoRaWAN for its long-range communication. LoRaWAN supports transmission distances up to 15 km in rural areas and 2 to 5 km in urban environments, significantly surpassing the reach of traditional Wi-Fi. This makes it perfect fit for use cases in smart agriculture, environmental monitoring, city infrastructure, and industrial IoT. Then for its ultra low power consumption. LoRaWAN devices are optimized for extreme energy efficiency, allowing them to run for up to 10 years on a single battery. This makes it highly suitable for battery powered devices in remote or hard to reach areas where frequent maintenance is impractical. Then for its flexible network infrastructure, LoRaWAN supports both private and public network deployments. This flexibility gives organizations full control over coverage, data privacy, and costs, unlike NB-IoT or cellular IoT, which may require expensive subscriptions and depend on third-party providers. Then for its ideal for sparse and scalable deployments, LoRaWAN excels in scenarios where devices are distributed over a wide area and need to transmit small data packets infrequently, such as utility meters, smart bins, or weather sensors. So, with its unmatched range, energy efficiency, and flexible deployment options, LoRaWAN is the ideal choice for scalable and sustainable IoT solutions across diverse environments. Now, let's talk about the things which are additionally offers by LoRaWAN. It offers license-free spectrum. LoRaWAN operates on unlicensed ISM, industrial, scientific, and medical bands. For example, 668 MHz in Europe, 915 MHz in US, eliminating the need for costly spectrum licensing. We can find the country-wise unlicensed ISM bands and the frequency plans from here. From the section 1.2 country cross reference table, under regional parameters of LoRaWAN technical specifications provided by the LoRa Alliance, which first released the LoRaWAN specification back in January 2015. So from here we can find the country-wise unlicensed ISM bands offered by the LoRaWAN protocol, which eliminates the need for costly spectrum licensing. Then it offers high network capacity. LoRaWAN network servers can handle millions of messages from thousands of gateways, supporting massive scale IoT deployments. Then it offers end-to-end security. Built-in advanced encryption standard AES 128 encryption ensures secure data transmission from the end device to the application server. Then it also offers low total cost of ownership. Thanks to low cost devices, minimal infrastructure requirements, and open source tools, LoRaWAN drastically reduces deployment and maintenance expenses. Then it offers thriving ecosystem. A robust and growing ecosystem of device manufacturers, gateway providers, software platforms, and network operators accelerates time to market and simplifies integration. So these additional advantages further cement LoRaWAN's position as a cost-effective, secure, and future-ready LPWAN technology. And together these features make LoRaWAN a compelling option for organizations seeking to build large-scale, reliable, and secure IoT networks with minimal operational overhead. Now that we know what are the advantages of LoRaWAN, what it offers, and how it can help us by overcoming the limitations of our Wi-Fi based IoT project, we can move forward with our discussion for upgrading our project with the LoRaWAN setup. And for that, let's first explore the infrastructure behind the LoRaWAN IoT ecosystem. For this, if we search for the word LoRaWAN, we will come across several key organizations involved in its ecosystem, such as LoRa Alliance, which governs the protocol and sets industry standards. However, when it comes to hands-on implementation and developer-friendly resources, one of the most prominent and widely referenced platform is the Things Network. It's a community-driven organization that offers free open source public LoRaWAN network designed to support innovation and learning. The Things Network is widely used by makers, students, researchers, hobbyists, and those running small scale pilot projects. It provides everything needed to get started with LoRaWAN, from documentation and tools to access to a global public infrastructure. Let's take a moment to explore their site. It's a great starting point to understand the core concepts of LoRa technology and how to build on it. We can find all the resources from here. You can see. So let's go back for the LoRa definition. So what is LoRa? LoRa is a wireless modulation technique. LoRa is a wireless modulation technique which encodes information on radio waves. What is LoRaWAN then? LoRaWAN is media access control MAC layer protocol built on top of LoRa modulation. It's a software layer which defines how devices use the LoRa hardware when they transmit, and also defines the format of messages. LoRaWAN is suitable for transmitting small size payloads like sensor data over long distances. LoRa modulation provides a significantly greater communication range and low bandwidth than other competing wireless data transmission technologies. And this is the diagram for the LoRaWAN networks architecture which we want to achieve for overcoming the lackings of our Wi-Fi based network for our IoT project, where we can see the end nodes as the IoT solutions integrated with the LoRaWAN devices: pet tracking, vending machine, smoke alarm, trash container, water meter. And there's a lot of, especially with the industrial IoT business solutions, about which we will talk later. And here we can see an example of a LoRaWAN end device which consists of sensors like temperature, humidity, and fall detection. And then we can see the gateways each gateway is registered using configuration settings to a LoRaWAN network server. A gateway receives LoRa messages from the end devices and simply forwards them to the LoRaWAN network server. Gateways are connected to the network server using a backhaul like cellular, 3G, 4G, 5G, Wi-Fi, Ethernet, fiber optic, or 2.4 gigahertz radio links. Here we can see an example of a LoRaWAN indoor gateway, and then there's an outdoor gateway for providing a larger coverage. The outdoor gateways are suitable for providing coverage in both rural and urban areas. Then after receiving the LoRa messages by the LoRaWAN gateways, the messages are forwarded to the LoRa network server, where it sends the messages to the application server for serving the user by maintaining security after applying AES 128 advanced encryption standard security technique, then validating the authenticity of end devices and integrity of messages, then deduplicating uplink messages sent by the devices, then forwarding uplink application payloads to the appropriate application servers, then forwarding join request and join accept messages between the devices and the devices join server, then selecting the best gateway for routing downlink messages sent from the application server while receiving for device related information and configuration, or changing the configuration settings of the device. Then sending ADR commands from application server to optimize the data rate of the devices. Then providing acknowledgements to the application server of confirmed uplink data messages. Then after receiving the uplink messages, receiving the uplink from the network server, the application server then decodes the messages and encodes when necessary using appropriate device drivers, then applies business logic, then provides management interface for managing the infrastructure components, then finally provides system and application integrations to serve the end user from different industries. Now let's talk about some essential concepts when working with the network server, LoRaWAN devices and gateways from the application server side. First, let's talk about the different message types used in LoRaWAN. LoRa messages can be divided into uplink and downlink messages based on the direction they travel, where uplink messages are sent by end devices to the network server, relayed by one or many gateways. If the uplink message belongs to the application server or the join server, the network server forwards it to the correct receiver. And then each downlink message is sent by the network server to only one end device and is relayed by a single gateway. This includes some messages initiated by the application server and the join server too. Now we will talk about MAC message types. So what is MAC and what is a MAC message? In LoRaWAN, the MAC, medium access control layer, is an integral part of the device's firmware built into the LoRaWAN stack. This layer includes a set of command types and control functions commonly referred to as MAC messages, which are responsible for managing and controlling the device's behavior over the air. These MAC messages play a crucial role in coordinating communication between end devices, gateways, and network and application servers. Now, some common LoRaWAN MAC message types are join request, which is an uplink message used during the over-the-air activation OTAA procedure to request network access. Then join accept, which is a downlink message from the network that accepts the join request, completing the OTAA process. Then unconfirmed data up, which is an uplink data frame where no acknowledgement is required from the network. Then unconfirmed data down, which is a downlink data frame sent by the server where no confirmation from the device is expected. Then confirmed data up, which is an uplink data frame where the device requests confirmation from the network, for example, guaranteed delivery. Then confirmed data down, which is a downlink data frame where the network expects acknowledgement from the device. Then rejoin request, which is an uplink message used to reinitiate the join process OTAA in case of lost connectivity or session expiration. So these are the LoRaWAN MAC message types, and this was about the LoRaWAN messages where we do have uplink and downlink messages, then MAC messages and their types. Now we do have adaptive data rate, ADR. In LoRaWAN, adaptive data rate, ADR, is used to optimize network performance and battery life by adjusting how devices communicate. It automatically manages spreading factor, SF, which controls range versus data rate, where higher SF or spreading factor equal to longer range but slower data rate. Then bandwidth, which affects how quickly data is transmitted, where higher bandwidth is equal to faster transmission but shorter range. Then the transmission power, which adjusts signal strength, where lower power saves battery and higher power improves reach in tough conditions. So the ADR helps devices use just enough resources to communicate reliably and efficiently. Now we do also have RSSI and SNR, where RSSI, received signal strength indicator, which measures how strong the signal is when received by the gateway, where higher RSSI is equal to stronger signal. For example, minus 30 decibels milliwatts, which represents a very strong signal, very strong signal strength, and minus 120 decibel milliwatts represents a very weak signal strength. And then SNR, signal to noise ratio, which measures signal quality compared to background noise, where positive SNR is equal to good signal and negative SNR is equal to noisy or weak signal, and higher SNR is equal to clearer communication. Together, RSSI and SNR help evaluate the reliability of LoRaWAN communication. So these are some of the essential concepts when working with the network server, LoRaWAN devices and gateways from the application server side. So these are the components which form an infrastructure for any public IoT solutions. As we said before, the Things network provides public IoT infrastructure which is widely used by makers, students, researchers, hobbyists, and also those running small-scale pilot projects. But for the business, it demands full private IoT infrastructure solutions where security is the first priority, and for that there is the ThingsHub IoT platform. ThingsHub documentation, then get started with ThingsHub. Then from the system overview we will find the architecture diagram of the ThingsHub IoT platform. So the ThingsHub IoT platform offers both private and public IoT solutions tailored to meet a wide range of industrial business needs. Here we can see the things which refer to the LoRaWAN devices, then the network servers, private, roamed, operated NB-IoT for cellular, and there's Sigfox based on the availability and infrastructure demands. And then we can see the network and connectivity connectors, which refers to the LoRaWAN gateways. And then on the application server side, there's REST API, device and user management, device drivers for decoding and encoding messages, time series data analytics for applying business logic. Then there's system and application integrators to visualize dashboard and also to serve the existing third-party enterprise IT systems. And all of these are delivered as a comprehensive IoT solution by the ThingsHub IoT platform, designed to solve tough industrial business challenges. And let me share my experience, my knowledge from the working experience. I worked 1 year for the device drivers development as a work student remotely for the ThingsHub IoT platform. Let's search for IO tracker, a LoRaWAN device, this one. Here we can see the IO tracker. This is the first LoRaWAN device for which I was involved in developing the driver with the responsible team from the beginning. A solid looking device, completely waterproof. This device is used to track indoor and outdoor positioning. A pretty small device. Here we can see its use cases: supply chain monitoring, emergency and safety, track and trace, and can also be used for the innovation. Let's quickly see the payload description for this device using which we wrote the driver for the device to use in the ThingsHub IoT platform for decoding the incoming and encoding the outgoing messages within the ThingsHub IoT platform. And for that we'll go to docs. Then from the docs we'll find decoding and uplinks. Here we can see the definitions and rules by maintaining which the driver needs to be developed for the decoding within the ThingsHub IoT platform to serve the users. And from here, these are the example payloads we can see. And from here, if we see examples 3, 4, this is the last one. So from here, if we see this last example payload, which we can receive in the ThingsHub IoT platform as an uplink, see what are the informations it includes. Button pressed means the panic button which is attached to it is pressed by a person, which sends a panic alert for emergency and safety purposes. Then moved means the vehicle or the object to which it's attached to is currently moved to a new position. Then GPS data included, which provides the moved positioning, GPS location of the vehicle or the object to which the device is attached to, which can provide an end-to-end tracking and monitoring for the supply chain management. Then there's precise temperature and light data included, which provides the monitoring of the environment surrounded to the device. So the driver is responsible to decode this kind of uplink messages to represent it as a human readable data within the ThingsHub IoT platform to serve its users. Now let's see what are the downlink messages are supported by this IO tracker device. And for that we will go for the configuration, and then under configuration we will go to downlinks. And here these are the definitions and rules which are used for developing the driver for the encoding within the ThingsHub IoT platform to send configuration request to the end device. Here we can see there's a lot of definitions and rules which are provided for this IO tracker device. Now if we see the provided downlink examples from here, downlink examples, here we will be able to see the different downlink examples for different kind of payloads. Here we can see the IO Tracker 3, IO Tracker 3 Pro. We will focus on the IO Tracker 3 device for these downlink messages. Here you can see there's lots of examples for the downlink messages. Enable buzzer alarm on device for 30 minutes, start GPS session for 30 minutes, 60 minutes, the responsible payload example which we need to send from the ThingsHub IoT platform to the connected LoRaWAN network server for sending it to the appropriate device. Then configure GPS stays always on. Then configure GPS start moving with max performance, reboot without configuration changes. Then request hardware and software version information, set battery level to full after changing the battery. Button configuration, enable light sensor, disable light sensor, enable accelerometer, disable accelerometer, set high sensitivity accelerometer, medium sensitivity accelerometer, enable temperature sensor, disable temperature sensor, disable Wi-Fi, enable Wi-Fi, disable BLE, enable BLE, Bluetooth, then disable humidity and pressure sensor, enable humidity and pressure sensor, enable humidity sensor, enable pressure sensor, enable man down detection. So these all are the downlink message examples which will be able to send from the ThingsHub IoT platform to the end device, which is IO tracker. So and we can see the responsible payload examples here. So the driver IO tracker is also responsible to encode these kind of downlink messages for configuration request sent from the ThingsHub IoT platform to the end device to make it readable for the device. So this was about the IO Tracker 3, IO Tracker LoRaWAN device, its device driver, and its communication strategies within the ThingsHub IoT platform. And there are some other LoRaWAN devices for which I was involved in with the responsible team to develop their drivers for the ThingsHub IoT platform from the beginning. Let's quickly see the devices. If we go to mclimate, and from the mclimate, if we go for the solutions they provide, from here the first solution, indoor climate optimization, let's go for it. And under here we can see the Wiki Smart Radiator Thermostat LoRaWAN device, and there's another one, the Wireless Thermostat LoRaWAN device. These two devices are for indoor temperature monitoring and heating control to optimize the energy cost. And there's another one, if we go for the solutions and then the air quality and CO2 monitoring. Let's go for it. And under this we will have another device which is mClimate CO2 display LoRaWAN. This device is for indoor environmental monitoring to control demand based ventilation inside of the smart buildings. So these are the devices from the mClimate, and there's another one for monitoring the water meters from Zener. Here we can see the LoRaWAN EDC communication module to collect, monitor and analyze the water meter readings periodically to optimize the usage cost. And there are some other LoRaWAN devices with which I was fully and partially involved with the responsible team to develop their device drivers. Now that we have introduced with some LoRaWAN devices, it's time to quickly talk about the LoRaWAN device classes. LoRaWAN defines 3 device classes to support different power and latency requirements. Here we can see class A, required for all devices. Device sends data, then briefly listens for replies, great for battery powered sensors, most power saving but slowest to respond. Then class B adds extra listening times using synced beacons, allows scheduled downlink messages, ideals for devices like smart street lights. Then class C listens all the time except when sending, needs constant power, not battery friendly, best for fast response devices like actuators. And here for these device classes, one thing to mention which is firmware upgrades, FOTA, typically require switching to class B or C to ensure reliable reception of large data packets. So each class offers, class A, B, C, each class offers a trade-off between power consumption and latency. We will have to choose the perfect LoRaWAN device to serve business IoT solutions based on the device's use cases. And here the devices which we have discussed, they all are battery powered class A devices. The devices which send data, then briefly listens for replies, and great for battery powered sensors, and required for all the devices. Class A is required for all the devices. So this was about the device classes, and there are lots of devices out there like this. There are lots of devices out there. If we want, we can find them by the Google search. It will be interesting to know about these LoRaWAN devices and their functionalities. As tech freak person like me, I already know about lots of LoRaWAN IoT devices theoretically, as I also worked on the drivers standardization for the Things Hub IoT platform. So we can go for that. So this was all about the LoRaWAN devices which are referred here as things and their drivers and necessary decoding and encoding by the drivers within the ThinkSub IoT platform. Now here the devices or the things are getting connected to the LoRaWAN network servers via the network and connectivity connectors, which are the LoRaWAN gateways, and then to the ThinkSub IoT platform. And then in here's some main functions which are there for the users or the business customers. Here we can see device management, user management, REST API. This is generally used by the developers to manage lots of things easily. Then there's device drivers to decode and encode LoRaWAN messages, about which we already talked about. And then there's time series data analytics for applying business logics to serve to the ThinkSub visualizer for dashboarding and its users or business customers. And then there's system and application integrators to serve the existing enterprise IT system based on their demand. And from this ThinkSub public documentation, we can know some more basic information about this ThinkSub IoT platform. So all of these components are delivered as a comprehensive IoT solution by the ThinkSub IoT platform to serve the businesses from different industries. This ThinkSub IoT platform is owned and managed by a Europe-based company named SmartMakers from Germany. They are currently one of the leading provider for IoT business solutions for different industries. If we visit their site, SmartMakers expert for IoT solutions. From here we can see they provide two types of IoT solutions, business IoT solutions, such as IoT asset tracking and IoT remote monitoring. And under solutions, here under solutions we'll be able to see the different industries which are getting benefited from these IoT solutions: car dealerships, automotive, components, chemistry and pharma, electronics industry, food, logistics service provider, aerospace, mechanical and plant engineering, medical technology, metal processing, special vehicle construction. So lots of companies from these industries are getting benefited from the IoT solutions provided by the SmartMakers. So this was about the SmartMakers, which is providing IoT business solutions with their ThinkSub IoT platform. The solutions can be through customer tenant with the infrastructure setup, or through on-premise deployment installation with the infrastructure setup, or through third-party system integrators with infrastructure setup. So finally, let's revisit our Wi-Fi-based IoT project. This is its current setup. So we can enhance and upgrade our solution following the architecture like as the ThinkSub IoT platform provided by SmartMakers. delivering a more efficient, secure, and reliable IoT infrastructure similar to what various industrial sectors are already leveraging through smart makers today.